Hello class and welcome back to Stanford Code in Place. This is week 2. Last week in week 1 we learned about Karel. We learned how to move, how to turn left, how to put the beepers and pick the beepers. This week we get to continue on with Karel for a second week, and we're going to learn more about how to write sophisticated programs through what's called problem decomposition. And we're going to try to tackle a fairly challenging problem using this. First, I want to review some of the things that we've learned this week. So this, I should show, is actually the problem. Welcome back, students, to Stanford Code in Place. This is week 2, and this week we get to continue with Karel, but we're going to do some program decomposition, which means breaking down a tough problem into smaller problems. First, I want to just briefly review some of the materials that you've learned this week. This actually is the problem that we're going to solve, and let's take a moment to look at the problem before we look at how we're going to look for resources to solve that problem. So Karel is facing this row, and then the second column is a pile of beepers. So every time you put a beeper, it will start adding a count for how many beepers. So somebody's put 4 beepers here. What they want us to do is spread that out over 1, 2, 3, 4 locations. So we're going to be thinking about how to do that as we look at some of the resources you've been given this week. The first problem I want to show you is from Chris's lecture on Mountain Karel. So here Chris has broken down that you need to ascend that mountain, you need to plant the flag at the top, and then you need to descend the mountain. So that decomposition is pretty straightforward, and it's not what I want to focus on. I'm not even going to go into the code. Instead, I want to look specifically at how you're able to figure out what is inside that loop. What does the loop look like based on pre and post conditions? So at first, when I saw this problem, I thought that Chris was actually giving you a version of the midpoint problem. Some of you may have noticed the midpoint problem was last week's extension problem, and it asked you to, in a world of arbitrary size, to figure out what is the midpoint and put Karel in the middle. And I thought that because, well, he's got this mountain that is centered in the middle, so don't you have to know where the center is? But then I realized, oh wait, Chris is actually giving you this structure here. You just need to walk up the structure. So that's a huge help, because we know from looking at the structure, how do we know when we've reached the top of the mountain? Well, it's because it doesn't look like the rest of the steps, right? There's no step up here. And so that is what we're using to figure out what is the end condition for a while loop. So when the front is clear, that is when we're going to be able to stop. We know that we've hit the top of the mountain. And so when you write this loop, you're going to be, while front is blocked, make a step up, make a step up, make a step up. But you want to make sure that the precondition, which is that Karel is at the bottom of one of these steps, and that Karel is facing east, is true for when you're done in the post condition. So now Karel is a step above and to the right and facing east. That's very important, because when Karel is moved up here, you want to be able to run that loop again. And that means Karel needs to look just like it did here, except moved up a step. If Karel's facing the wrong direction, it's not going to run right. So, and it's pretty much true for going down again. So going down, we're always looking at an empty wall ahead of us here. Empty wall, empty wall. Here, now the wall is blocked. So while front is clear, we continue to do this move down and then stop. And again, the pre and the post conditions are important. You have to know which way Karel is facing at each point. So that's Mountain Karel. Let's take a look at the next problem they covered. This one was called Roomba Karel. So Roomba Karel, there were lots of different solutions that they proposed. Here's a really wild one. This one is actually one that I would have thought would have been a good way to do it. Let's see, they also had this spiral idea. Now, let's take a look at the spiral idea for a moment, because we do need to be thinking when we look at these possibilities for how do we actually make this work, and how do we stop? So thinking back to mountain, Karel, we knew that we could stop going up when there was no wall in front of us. In this algorithm, yeah, okay, so we can run to a wall and then turn left, run to a wall, turn left, run to a wall, turn left. Now, here we can't run to a wall, right? Because we're going to have to stop short. So we're going to have to modify that to run to a wall or a beeper and then turn left. And then run to a wall and turn left, run to the wall and turn left, run to a wall and turn left. And it does seem like you could make something work. You're going to have a while loop that has multiple conditions, and it's a bit tricky. This one here, I like this one that he didn't go into, and I actually did a problem called Build a Mountain that uses a very similar path to this, and there's a complication that I found. So you have a loop that basically says you go to the end, and when you hit the end, go up. The problem is that going up on the right side is a lot different than going up on the left side, right? And also, you have an end condition when you can no longer go up. But that end condition could be, if you're facing this way, it's going to be on your right. If you're facing this way, it's going to be on your left. And so I actually had to create new methods instead of turn around. I had to ask Karel, which direction are you facing? So when I move up, if I'm facing east, that means I'm turning left. If I'm facing west, turning up means turning right. So you have to make your loops consistent. And so in order to make my loops consistent, I had to create new methods for turning up so that I could just say turn up, because you don't want to have a loop where sometimes you need to turn right and sometimes you need to turn left. That's not a good idea. All right, so let's get to the solution that they did say was the simplest, which is you go down and back. And the reason they chose this is because it has the simplest pre and post conditions. In other words, you're always at the left whenever you're starting. This is going to be the start of your loop. This is going to be the start of your loop. This is going to be the start of your loop. And each time you're facing left, and each time you can check, is there something to my Karel facing this way? So left is actually up, and that gets a little confusing, but it's the case. So it's always the same going up. Now, I want to take a brief detour and talk about these pre and post conditions, because when I was in college, I actually had an instructor who designed a language called CLU, C-L-U. It was never used by anybody else. She designed it specifically as a training language. And this is my instructor, Barbara Liskoff. And she is one of the few people in history to have won the Turing Award, which is basically the Nobel Prize for Computer Science. And one of the things she did in the CLU language was introduce this idea of pre and post conditions. In our CLU language, every time we wrote a function, we literally needed to say to the compiler, what is the preconditions? What are the post conditions? And it was a very tough language to write in because we had to guarantee that those things are true. But that's actually where these pre and post conditions come from. And actually, Barbara Liskoff did her PhD at Stanford. So now that we've talked about pre and post conditions, let's go forward to the problem and let's see how we can use the pre and post conditions to make this help make this smoother. And I have to warn you, this is a tricky problem for what we call the end conditions. It's not real friendly. Let me explain by going and doing a little bit of a simulation for you. So here's a slightly different example. I did 5 instead of 4 beepers. And let's see what happens. So Karel is going to come forward and walk here. And then he's going to pick up a beeper. So we'll decrement that to 4. And now Karel is going to put a beeper here. And then Karel is going to come back to here and see that there's 4 beepers. So he's going to pick up 1. So now there's 3 beepers. And then Karel's going to have to walk over here and put a 3rd one there. Then Karel's going to come back here, decrement to 2 beepers. You know, I need to move Karel over here just so you can see what's going on here. 2 beepers, and Karel's going to put 1 here. And then Karel's going to come over here and pick up 1 of those beepers and put 1 over here. So now we started with 5, if you remember. So now we got 1, 2, 3, 4, 5 beepers. So question is, how do we know to stop here? So if we think back to the to this Roomba solution, Roomba had this ability where it was always facing east, and when you got to the top, you could say, is left clear? You could say, is left clear at all these points, and it'll always be false until we got to here. And even then, it was slightly tricky because once the left is clear, we want to stop, but we still need to fill this row in too. Okay, but coming back to here, we can check if there is a beeper present here, but we actually want to stop because we've gone from 5, 4, 3, 2, 1, but we still can't stop until that beeper actually goes away. So we can check here while beeper's present in this 2nd spot to stop the loop. But a little bit similar to Roomba, once it detects that the left is no longer clear, we still need to do something. In Roomba's case, it had to fill in that whole row. In our case, we actually now have to put the beeper back. Okay, but that's the special end case. It's only because Karel can't actually count how many are there. We actually have to go 5, 4, 3, 2, 1, 0. Now we can stop. And then we have to put the 1 back in. Okay, so that's an important note. So let's put that into the code comments right now. So stop when 2nd column is empty, but we need to actually put back 1 beeper in 2nd column. So we know that we're going to have to stop when the 2nd column's empty, and we're going to put the beeper back. Okay, so what happens inside of this loop? We're going to roughly have something that says draw the row by picking a beeper and putting it at end. So again, let's go through the simulation. Let me delete these beepers. And just for brevity's sake, let's say that there are just 3 beepers. Okay, so Karel is going to walk over here and then check, is the 2nd column empty? No, so then it decrements the beeper. It's actually hard to read now. I think does that say 3? It does say 3. Okay, so Karel's going to come over here. Then Karel's going to decrement that 3 and put 1 over here. Then Karel is going to decrement that from 3 to 1 and then put 1 down here. So each time we have to walk forward until we find an open space and then put a beeper. So let's write a function that's going to do that. I'm just going to call it draw row for now. And the point of draw row is to it's actually this right here. Let's just put that comment in there. We'll replace this by actually calling draw row. For now, I actually need to keep that indent. Okay, so draw row. So we're going to find an open space, and we're going to put the beeper. And we also need to pick up that beeper. So again, let's review. Let's get rid of these. Karel here. So we've got to move Karel over to pick up the beeper. But let's think about, where do we want to do this operation? So we're always checking the second column. That's the column where the information is. And it's also different than from Roomba Karel. Karel was always the first column. And that's actually pretty simple because it's easy to find your way to the first column. Second column, it's you got to take one more step. So, but what if we always came back to the second column and not the first column? That would be convenient, so that every time we come back, we're already sitting on where we need to be. So let's have a precondition and a postcondition be second column facing east, second column facing east. And we'll say after here, the beeper was decremented. One more beeper at end. Okay, so we're going to pick a beeper, find an open space, and put a beeper. So let's try. Oh, you know, I'm doing this. Well, I've got my own world here, but maybe that's. No, let's go ahead and let's do it in the world. Let me copy this code. Okay, this is spread beepers here. So let's go ahead and replace this main. Okay, I got too many def mains. All right, so let's try to make draw row happen. So now the pre is at we're in the second column, so we actually need to do a move. So we're going to move, and we're now in the second column. So now we can just actually act. So we're going to pick beeper. So if, let me reset this here. So if Karel is on the beeper, which we pick up, and it becomes 3, then to find an open space, we are going to, presumably we might have multiple of these here. So while beepers are present, we're going to move forward. Let's just see whether it's going to stop. Okay, so it stopped there. That's good. If there were multiple beepers there, they would go farther. So then finally we need to put a beeper. So it should spread this out. Okay. Now, I would like to be able to just call draw row a second time. But the problem is that we're not ready to run this again. Because remember, our preconditions, we're in the second column facing east on top of beeper. So I need a function in draw row to move to second call. Actually, let's just call it the function name. So we're going to have to turn ourselves around, and I've already got. Oh, I don't have a turnaround here. So let me. Let's quickly do that. So we're going to turn around, and then what's the condition we want to stop at? While beeper's present. Now we could do while front is clear. We'll go all the way back, and then walk forward another one. But while beeper's present is going to work for now. Okay. So pre and post here could be any column facing east. The post is going to be second column facing east. Now I just talked about beeper's present is going to work. It's going to work while we have 3, when it's 2, and there's 2 more here, when it's 1, and there's all these spread out. But when we eventually get to 0, it's not actually going to work. And that's something that you actually probably have to play with to understand. When it gets to 0, it's not going to work. And then, so we are going to have to use the other choice, which is while front is clear, we're going to come all the way to the end. We're going to turn around, and we're going to move back to the second column. So let's see if this one draw row works. Oh, we actually called it twice here, didn't we? We did call it twice. Let's see what happens if it works 2 more times. And let me speed it up. Okay. We got to the point where it drew 4 rows. Now we've got to stop when that second column is empty. So this is where we now need a while loop. That while loop is we're on the second column here. So while the beeper is present, we're going to call draw row. Let's just see what happens there, because we're not quite done yet. Okay, it keeps on going back and forth. Why does it do that? So let's go the very first time that it hits that fourth loop. And then we come back, turns itself around. Okay, right here. So it's checking while beepers are present, draw the row. It picks the beepers. Now, while there's an open space, it's just going to go, there's no beepers present. It's going to try to move the beeper down there, but because there's no beepers present, it's actually going to put it back. So now we're in the same position we were before. So it's going to keep on doing it over and over again. So we actually don't want to draw the rest of this row. And this is another oddity, because the whole point of this function is to draw the row, right? And in this case, you're not going to draw the row if you are on the last beeper. You're basically done. And that's an oddity. That's a challenge for people to figure out. So we're going to pick a beeper. So instead of doing this while beeper's present move and then put beeper, we need to do a check. And if the beeper is not present, we don't want to draw that row, and we want to leave ourselves in a place where the loop is going to stop. So how can we do that? And here's the third trick of this problem. In order to make it stop, what we can do is we can go back to the column 1 where there are no beepers present. Then when this test happens, it will fail and stop. So what do we need to do here? So right now we're putting beeper, and then we're moving to the second column. Okay, what if we move to the first column instead? Well, the problem is that we need to do the check before we put that beeper there. So we need to have an if statement here. If beepers present. And if the beepers are present, we want to do this code. If the beepers are not present, then we need to restore the last beeper. And we need to set up to end the loop. So to do that, we want to go back a step. So we have a couple of places to do this. It's dangerous to do this in this loop. But yeah, it's kind of unfortunately required. So what we need to do is back up a step. So let's define a simple function here to let's do it down here near the turnaround. And that's going to be a turnaround, move, and turnaround again. Let me put that in. Oh. Back up. Okay, so let's go to. I guess we gotta run it, and I'll stop it. Okay, let's go back and see what happened there. Okay, so we're in the last execution. So we pick the beeper. If beepers are present, we don't do that. Instead, we put the beeper back, and then we back up. Let's see what that looks like. We turn around, and we're there. Now where did we go? Now we're back to the while beepers present. While beepers are present, it skips drawing the row. So that actually is all the code that's necessary. Oops. Get rid of that pass. So we didn't need to put the beeper back because we did it right there. We can get rid of this comment here, but the alternative is we could have actually changed draw row. I just called it draw row to start. We could change that draw row to draw rows and put this while beepers present actually in here. It's kind of an obscure reason why that's better, but it actually is, because I don't like the way that this function is communicating with the previous function. I'd rather that all happen in the same function, but for these purposes, it's fine. Let's go ahead and delete that. So I thought a little bit more about what's going on here, and I had a realization that we really do need to actually do it in here, and I'll tell you why. Remember these pre and post conditions? Right? We were supposed to, the post condition was supposed to be we're in the second column facing east. We did not meet that post condition. So the way to handle that is we're actually going to have to do this. We're going to have to take these while beepers present, put it in here. So we're going to do the while beepers present. We're going to put all of this. Now we're going to have to tweak this code a little bit. So while beepers present, we're going to pick the beeper. If beepers present, so while beepers present, when we're done, we're going to do the backup outside. So the last execution, it pulls the beeper, then it tries to put the beeper, and finally it will back up. So now we have a little bit different look. So now we're going to move, and then we're going to draw rows. Okay, now, with any luck, that actually is sufficient to change this. Reset. Run. Wait, it's got an infinite loop. Okay, so why is that? Let's go back. Comes back. Okay, while beeper is present, pick the beeper. If beeper is present, nope. So it's going to put that beeper back. Oh, yeah, okay. So we need to back up. We actually need to do the backup in here. Put the beeper back and back up. Let's try that now. Yeah, that did it. All right, and let me just review for a second. Now, remember when I said that Clue was a really difficult language to program in? This is exactly the reason, okay? Right, because you have to guarantee that your pre and post conditions are actually true. And so clearly it would have forced me to do this. It's still a good idea. Obviously, in this program, it was fine to do it either way because in the end, it got the job done. But if this program were to be in a larger program then and used elsewhere, then these pre and post conditions are very important. So once I wrote this contract, that means that anybody, it's not really a contract, right? Chris calls it a contract. It's not a contract. Clue, it's a contract. Here, it's just a comment to the coders. But once you do that comment, people will assume that. And if you want to be a professional or do a big project, this is true. And so you need to guarantee that that actually is going to be true. And so I couldn't guarantee those. Sorry, this is actually the wrong column. It's the wrong thing. It was up here. Draw the rows. So I couldn't guarantee that was true anymore. So the pre is we're in the second column facing top. The post, we're actually going to be no longer in the second column. We're going to be in the first column facing east. Beeper, decrement, winner. So, and what's also true is that second column has only one beeper. Okay, that is the new post. All right, so that's all she wrote. Sorry that this problem had several different one-offs in it, but hopefully through the experience you can get a better sense for both, if you just start writing the code, what's going to happen. I didn't go through all that, but I talked about it, versus if you actually analyze ahead of time and then lay things out to meet those conditions. So good luck to you this week, and we'll see you again next week.